Hello, this video is targeted towards programmers and non-programmers wanting to grasp HTTP, HTTPS, and web servers. I've implemented enough of the HTTP protocol itself to support my project. This video assumes the presence of a TCP/IP implementation on your system. We won't be writing TCP today, just HTTP at the application layer. I also have HTTPS with TLS, otherwise known as SSL, which I'll touch on. I learned this by writing code and reading the on-screen documentation. Here, the Hypertext Transfer Protocol, RFC, for HTTP 1.1. You can find it at this link or just by Googling the RFC for HTTP. And this is a useful web page from developer.mozilla.org where they give a more digestible overview of implementations of these protocols, which I found very helpful. So, lastly, we'll be looking at a little bit of C code, but I aim to be mostly language agnostic. Right. So, we have two computers here with a cable between them, drawn artistically. Protocols. Protocols are interpretations of data. What does that mean? So here is the string hello, interpreted as a sequence of bytes, which are themselves a sequence of binary electrical signals called bits. If you're watching this, you're likely aware of this. But this sequence of bytes does not need to be the string hello. That is an encoding made by us to imbue the sequence of bytes with meaning. This interpretation is useful to us to carry legible text from the computer memory to a reader's brain, for example. The same sequence of bytes could be interpreted differently. Perhaps we want to do a computation. This interpretation, where the sequence is a big number, could be useful when we want to do some arithmetic operations. That is the essence of a protocol, an interpretation of data. So, back to the main topic. HTTP runs over TCP. What does that mean? Here is a subset of the OSI model called the TCP/IP model. If you're training as an IT employee or otherwise work with computer networks, this will look familiar. I would expect at least a vague familiarity with this diagram and network addressing. Know what an IP address is. This is the stack of protocols that a HTTP message travels through to be transported from one compliant application running on a computer to another compliant application running on a different computer, typically. So, what does it mean for data to traverse the stack? What does it mean for software to be compliant? So, each of these layers is another interpretation of the data performed by the computer. As a contrived example, we start here at the top with a HTML web page, and we want to get from a server. So there we go. So we will use the HTTP protocol to write the data that we need at this level, the application level. So in this case, the name of the HTML file that we want. Let's write that into computer memory as a string, like we saw down here before in this buffer. The string with the name of the file that we want. That'll be our contrived HTTP protocol here. So we also need the TCP IP address of the server. We can write that into our packet. We'll call this a packet or a message. The terms can be used interchangeably. We'll write this into our packet as well as an integer. So we can, let's write it as an integer next to our string that we already have. And yes, an IPv4 address is a 4-byte integer in the real world too. We write our own IP there so the server we send this to knows where to send the response. We also need the MAC addresses. Let's write that next to the two IP addresses as integers. That we have as integers and the URL string, not the URL, the HTML string that we have here. we've written all the data we need into some memory in a specific order and length. A string, then two integers, and another two integers for the MAC addresses. At the physical layer, we encode, uh, that's a keyword. This is once again a protocol. We encode that into an analog electrical signal that can travel along an Ethernet cable, an actual copper Ethernet cable, to another computer, which expects the data in the specific format and interprets it, putting the data to use. So the other computer has gotten all the data and it needs to open the HTML files that's on its file system and send it back to the client address. And because we formatted it in the specific way as a protocol, the server not only has the data it needs, but when some pre-written software running on the server interprets it in that specific way, it sees the data in a form it can use. In this case, to load and send the HTML file. That's what it means for a protocol, for a program to be compliant with the protocol, or rather, the standard that defines the protocol. It can extract useful information from the bytes of data that we've laid out according to the protocol, so that if two computers are on the other side of the world running different software, as long as they read the bytes in an agreed upon fashion, it can be processed in a useful way. For example, to fetch a web page and then interpret that standardized HTML data with the browser software to draw a pretty web page on the client computer from the data we fetched. So, as a side note, the IP and MAC addresses may look redundant here. This is because of routing and is beyond the scope of this video, but you need them both. As a second side note, you may have heard of TCP UDP ports. To summarize, the IP address locates a computer in an internetwork and is part of the IP layer, while the port locates a specific application or executable running on a computer and is here on the transport layer. But they both are represented by a single integer in the real world. So as a as a final subnote, why are there layers? Couldn't we write and interpret all that data at once into a message in our humble application? Yes, but we'd need to make the Ethernet and TCP IP software ourselves, our own OS, so to speak. Regardless of the approach, even if we were to do this, they are distinct layers still. They are distinct because they are independent protocols that are interpreted differently, even if you do all the reading and writing within the same program, for example, in a virtualized environment. Congratulations, that's the TCP IP stack, and for all intents and purposes, the OSI model too. The real protocol in the real world looks exactly like this, only with a lot more data appended per layer. And the data that you add at each layer as you go down and up the stack, down the stack, are called headers, by the way. So, here is a HTTP request and response taken directly from my browser. That's all it is. These literal strings sent over the transport layer, the TCP protocol. The string headers here just give my server information I can process and use to build a response and or do other computations. In my implementation, I ignore most of the fields here in the request header. So, here is the response, exactly as it would be sent over the network. Note the new line and carriage return characters. This is exactly like the string we were just looking at over here on the first slide. That's how these characters are written there, except with new lines between each piece of information that we're writing, and then one more new line directly before the data we want to send. In this case, it's this HTML page, and this opening bracket over here is going to come directly after this new line over here. That is the data as it would be sent over the wire. It's that simple. It's just a string. So, TCP, here are the methods. This may look familiar. These are the function calls used in the communication, and they correspond roughly to what you as an IT trainee or programmer might be familiar with, or network engineer. The old TCP handshake down here. This is what we're doing with this listen function. Then the client attempts to connect, then the server accepts it, and then they can send and receive an arbitrary amount of data between accepting the connection, and then when either side is done, they send a close packet, or they time out. They could also time out, at which point this TCP session ceases. So, I said I would touch upon TLS. TLS is security at the transport layer. This encrypts all of the data contained within the TCP header, also within the TCP packet between the headers, or after the header, the HTTP information, as well as the HTML web page we have in there. That is all encrypted with the transport layer security. And when we are using this feature, we append an S to the HTTP to denote that we're using these encryption features. So it looks a little bit different with these encryption features. We do the completely standard TCP handshake. Then we exchange these encryption keys so that all the subsequent data can be encrypted. Now, from the application programmer's point of view, from my point of view as a HTTP implementer, these TCP functions I have here, which I get from the operating system, by the way, these will look similar on Linux and Windows, or other operating systems, assumedly. These are replaced with TLS or SSL counterparts. TLS and SSL, by the way, as a side note, are the same thing. SSL is just the outdated old name for the concept that we're talking about, and TLS is the current name, Transport Layer Security. And you'll see this come up a lot. For example, the library that I use and a lot of people use to implement this encryption is called OpenSSL. And as I was just saying, it swaps out these TCP functions that I call from C, but there will be bindings to these functions for pretty much any programming language you might choose to use. And yeah, you'll just get these swapped out one-to-one with encrypted versions if you're using OpenSSL. You could also implement it yourself the same way, technically. Nothing's stopping you, but that's beyond the scope of this video. So that's where the encryption and the HTTP, the S part of HTTPS comes in. The actual HTTP protocol itself is completely untouched. It's, to me, even as a low-level programmer, a low-level application programmer, this is all completely transparent, or opaque, rather. I don't have to worry about any of this stuff as a programmer. And yeah, it's very simple. It's just these strings that get sent across the network. And to reinforce that concept, we'll look at the actual code that I've written. Here's the HTTP handler itself within my code. If you can't understand this, that's not so bad. You can shut your brain off for this section of the video. So here are the request headers as we've gotten them from the client asking for this resource, this image, for example. And that's important to me. I as the server, I want to know what I want to give the client. So I know this protocol. I know I'm going to expect this get over here at the very first as the very first thing that I get from the client in this string, the very first byte that I receive will be this get here. So that's exactly what I look for on the server. It's this agreed upon, almost secret code or own language that they agree. That's HTTP. So I've extracted these bytes from the TCP message that I've gotten at the operating system level, and now I'm just reading this string, one character after the next. And here, the client is running a GET request. That's part of the HTTP standard. You may be familiar with this if you're watching this video. And in the case that the client wants something, we authenticate them. Complicated process, not important over here. And we have these various authentication conditions, and we'll, in all likelihood, send content to the client, at which point we construct our response header over here. You can see that this is the same response header that I have over here, back on the slide. So we write this exact string, character for character, into that buffer, into the message that we want to send over TCP. The operating system and underlying libraries handles TCP for us. Send data TCP, I wrote that function myself using the operating system utilities and using these send and receive functions that we saw earlier. I can look at that quickly. Here it is, send TCP encrypted. This is where we end up. SSL write. Like I said, it's and here's the TCP send function. This is just the encrypted version of that function over here. That's where it end. That's where the function calls end up. That's TLS. That's it. And yeah, we write this header. We write one more new line, and then directly the HTML data afterwards. And the client knows what to do. The browser knows how to use that data, and it knows that we just want it drawn real pretty and formatted in front of us, and that's it. HTTP, just a string. So, in conclusion, this implementation is a minimal working example. It's probably insecure and definitely inefficient, but it works. Here is my web page loading. If I compile and run the software, actually I'll do that in front. Here's the compilation, and I will rerun it from the beginning. There's the server running on the local machine. And we can see HTTP requests going through here. Here's a bunch of them as the page loads. And yeah, there we go, HTTP implementation. And that's what we get shown over here. We can look at it in raw form. That's just the string, and as a server, I need to parse that character for character and figure out what to do. I ignore about 90% of everything I get from the client. I don't need most of this. And yeah, keep in mind, this is all HTTP 1.1, not HTTP 2, not HTTP 3. Those protocols convey almost entirely the same information, but formatted differently. They're updates to the HTTP standard for performance and are outside the scope of this video. The project is linked below. I hope this information was helpful. Have a nice day.